In this video, we will learn how to name ethers, aldehydes, and ketones. Note that ethers look kind of similar to alcohols, but instead of having an H group on one side, there are R groups on either side. And these R groups can be any hydrocarbon chain. So in the example in the bottom, you can see that there are two ethyl groups. And because they are connected by an oxygen in the middle, that's an ether. Aldehydes and ketones both contain what we call a carbonyl group. This carbon that is attached to an oxygen via a double bond is a carbonyl. And on either side of that carbonyl, we can vary the substituents. On the left side here, we have an R group that'll be some kind of hydrocarbon chain. And in the example in the bottom, it's 3 carbons long, but that could vary. And on the right-hand side, there is a hydrogen. If you see that kind of format, that's an aldehyde. Ketones, on the other hand, will have a carbonyl in the middle, and on either side, they will have an R group. And those R groups could be the same length, or they could vary. In that example in the bottom, you can see that one of them has 3 carbons, whereas the other one has only 1. Still a ketone, it doesn't really matter how long that particular hydrocarbon chain is. The first thing we'll do is name ethers. And for ethers, there is an IUPAC naming system, but we're not going to use that. We're going to use the common naming system, which is very simple. This one's pretty nice. The first thing we will do is name the alkyl group on either side of the oxygen. And once you have that, all we're going to do is list the alkyl groups in alphabetical order. And finally, we will tack on the term ether at the end. All right, let's take a look at an example. We can start by using the example we saw on the top. All I'm going to do is identify these alkyl groups. And I see that either one has 2 carbons, which means they are both ethyl groups. And anytime you have 2 of the same substituent, we're going to use the prefix di to indicate that there are 2 of them. And then if this is diethyl, all we have to do is add the term ether at the very end. And these are actually separate words, so we're not actually compressing these together like we did with everything else. So this is called diethyl ether. And that's it. It's a pretty straightforward naming system. Let's try another one. Okay. I'm going to identify the alkyl group on either side of the oxygen. The one on the left has 3 carbons. I will call that propyl. The one on the right has 1 carbon, which means that's methyl. And then all I have to do is list them in alphabetical order. Methyl will be alphabetized by M. Propyl will be alphabetized by P. Well, M is before P, no alphabet. So this will be methyl, propyl, ether. 3 words. All right, let's try a slightly more challenging one. Okay, so this one's a little bit tricky because you need to be able to identify the substituents, but it's not too bad. Okay, the one on the left has 3 carbons. But notice it's not just a regular propyl, because in propyl, we saw that they were connected in a 1, 2, 3 pattern. This one is what we call isopropyl. It's attached through that middle carbon. The one on the right has 4 carbons, so it'll be some form of butyl. And note that this is a tertiary carbon, so we call this one tert-butyl. And here's where we have to be a bit careful. The prefix tert is not considered when we're alphabetizing. So tert-butyl actually gets alphabetized by B. Iso is included when alphabetizing, so that one gets alphabetized by I, which means that tert-butyl will be listed first. And that becomes tert-butyl, isopropyl, ether. And that is it. I think the most challenging part here is really just recognizing the different functional groups. Let's name some aldehydes. Okay, so the first thing we will do is number the carbon chain. As usual, we'll find the longest continuous carbon chain. We have to make sure that that carbon chain contains the aldehyde. We'll number the carbon chain starting with the aldehyde end. So the aldehyde has the highest priority here. It will be more important than any of the substituents. So we'll start numbering on the aldehyde end and end the name with al to indicate that it's an aldehyde. And since the aldehyde is always at the end or beginning, however you want to think about it, is always at the end of the chain, it is always carbon 1, which means we don't need to indicate that. So no need to indicate carbon number because it's always carbon 1. And that just has to do with the structure of aldehydes. We saw that aldehydes need to have this kind of format where they have a carbonyl, a hydrogen on one side, and then an R group on the other side. Well, if the hydrogen has to be at the end, that means we can't have any more carbons on that side, which means the chain will always start on carbon 1. Just structurally, it has to be that way. If we change that hydrogen to another carbon chain, well, then it becomes a ketone. So with aldehydes, we have no choice but to call that carbon 1. And since we're at it, let's just go ahead and name this aldehyde. I see that it contains 6 carbons in the chain. If this was just a regular alkane, we would call it hexane, but it's an aldehyde, so we'll change that E ending to al, and that becomes hexanal. And again, I don't have to specify one hexanal because it's understood that that will just be carbon 1. Keep in mind there's one aromatic aldehyde that you will need to know, and that is benzaldehyde. If you see this as the parent, then the parent name will be benzaldehyde, and the aromatic carbon that is directly attached to that aldehyde group will be carbon 1. Be careful because sometimes students make the aldehyde carbon 1 and then the numbering gets very confusing. You do not want to do that. You want to make sure that the aromatic carbon attached to the aldehyde is carbon 1. Okay, let's try a few. Okay, I'm going to locate the longest continuous carbon chain, and that is 6 carbons long. So the parent will be hexanal. And then I need to list the substituents. I'm always going to number to give that carbonyl carbon 1, unless it's aromatic, but in a linear chain, it'll be carbon 1. And then I'm going to continue numbering down the chain. Then we have 2 methyl groups, which means we need to indicate that there are 2 of them using the prefix di. That will become dimethyl. And those methyl groups appear on carbons 3 and 4, which means I will call them 3,4-dimethyl. And then I put all of that together into one word. And that becomes 3,4-dimethyl hexanal. And that's it. Let's try another one. Okay, as usual, longest continuous carbon chain. I'm going to start numbering at that carbonyl carbon and then continue toward the end. There are 5 carbons here, which means the parent name will be pentanal. And then I'll list the substituents. On carbon 4, we have 2 methyl groups, which means this will be 4,4-dimethyl. On carbon 2, we have a substituent that has 2 carbons, which means this is ethyl, and I will call it 2-ethyl since it appears on carbon 2. Keep in mind that the prefix di is not used when alphabetizing, so we're actually alphabetizing by M, and for ethyl it's easy, it's just one letter, so we'll alphabetize by E there. And then we put all of that together, and that becomes 2-ethyl 4,4-dimethyl pentanal. Let's try one aromatic one. All right. There is definitely an aromatic aldehyde here, which means right off the bat, the parent name is benzaldehyde. And the carbon directly attached to the aldehyde gets carbon 1. And then I need to decide whether I'm going to number clockwise or counterclockwise. If I go counterclockwise, the next substituent is on carbon 3. If I go clockwise, the next substituent is on carbon 2. So I prefer that option. And I will continue down the chain. And then I'll name the substituents. This one contains 1 carbon. So that will be 2-methyl. And this one has 3 carbons that are not connected together in a straight chain. That is 5-isopropyl. Keep in mind the prefix iso is considered when alphabetizing. So isopropyl will be listed first. And that will be 5-isopropyl, 2-methyl benzaldehyde. And that is it. Let's take a look at our ketone naming rules. We are going to find the longest continuous carbon chain that contains the ketone, as usual. And then we will number the carbon chain to give the ketone the lowest possible number. So here the ketone takes priority even over substituents or anything else. We will change the ending of the parent name to -one to indicate that it's a ketone. And then we'll indicate the location of the ketone numerically. So you're going to list the carbon number of the ketone. Unless it's cyclic. If it is a cyclic ketone, well then the ketone carbon is always carbon 1, which means there's no need to indicate that numerically. Let's try a few. I'll start with a cyclic version. Okay. It is a cycle of 6 carbons, which means if this was a regular alkane, we would call it cyclohexane. But we're going to change that E ending to -one to indicate that it's a ketone, which means the parent name becomes cyclohexanone. we will give the ketone carbon 1 because it's cyclic and we want the ketone to have the lowest possible number. And then we could either go clockwise or counterclockwise. If I number counterclockwise, then the next substituent gets carbon 2 versus carbon 3 if I went clockwise. So I'll go counterclockwise and then just continue down the ring. And then I'll name the substituents. This one contains 2 carbons. That'll be 2-ethyl. This one has 1 carbon. That will be 5-methyl. And then I just list them in alphabetical order, and E is before M. That will become 2-ethyl, 5-methyl, cyclohexanone. And again, I don't need to indicate the location of the ketone because it will always be carbon 1 if it is a cyclic ketone. Let's try a linear example. Okay. So here we want to be careful. It is very tempting to always just go directly across to find that longest chain. And if I did that, I would have 1, 2, 3, 4, 5, 6, 7 carbons. I'm not really paying attention to which order I'm numbering in. I see that there are 7 carbons. But if we continued further up the chain, we actually have a longer path length. Now we have 8 carbons. So you want to be careful. Make sure that you're always selecting the longest continuous carbon chain. So since we have 8 carbons, the parent name will be octanone. Now I will need to indicate the location of that ketone because this is not cyclic. It's not going to be on carbon 1. But first I need to figure out which way I need to number, and then we'll go from there. Keep in mind that we're prioritizing the numbering of the ketone, not the substituents. If I go left to right, the ketone is on carbon 4. If I go right to left, the ketone is on carbon 5. And I want to give the ketone the lowest possible number, which means the version on the top is the one I want, not the one that gives a carbon 5. Now that I have that, I'm going to name the substituents. And it looks like we have a couple of methyl groups here. They appear in carbon 6 and 2. So that will be 2,6-dimethyl. And I do need to indicate numerically where the ketone appears. It's on carbon 4, so that becomes 4-octanone. And then I put all of that together into the final name. All right. Let's try one more. Okay. The longest continuous carbon chain here will be 6 carbons long. Keep in mind, I could have counted down or to the right. It really doesn't matter. It will be the exact same number of carbons. And then I need to figure out the numbering system. And here I want to go left to right to give the ketone the lowest possible number, not the substituent. So I'm going to number left to right. And the parent will become 2-hexanone. 2 to indicate where that ketone is. Hex to indicate that the longest chain is 6 carbons long. And then -one to indicate that it's a ketone. And then I'll name the substituents. On carbon 4, I have a chloro group. I will call that 4-chloro. On carbon 5, there is a methyl group, so I'll call that 5-methyl. And then I will put those in alphabetical order, and chloro gets listed first, which means this becomes 4-chloro, 5-methyl, 2-hexanone. And that is it.